The topic this week and next week is demand response. Demand response is about adapting the consumption in electrical grids as opposed to adapting just productions. We will do it in two parts. First, we will see further topics on optimization, because demand response is classically leading to model predictive control type of optimization problems. So we'll say a few words today about model predictive control. Then when this is done, we'll go more into a description of what demand response looks like today or might look like in the future, and do a bit of theory on its economical impact aspects. Before we dive into the topic, let me poll you with your background on MPC. Okay, I close the poll. So the majority never had a course on MPC or doesn't know if you had a course of MPC, which is consistent. If you don't know what MPC is, you can't know whether you had a course on it. Probably it means you didn't have a course, otherwise you would know what that means. But 40% of you had a course on MPC. Well, the good news is that we won't do a course of MPC, but we'll do everything we need to know about MPCs, because after all, this is an almost straightforward application of optimization. If we want to do analysis of why MPC works, that's a different story. But writing an optimization problem as an MPC is immediate, and solving it is of the same nature as we saw last week. So the main difficulties we had, or the absence of difficulties we had with optimization problem, will be the same here. So what is an MPC? An MPC is, the key word is receding horizon. We can view it as a method to provide a policy. In the optimization problems we saw last week, we didn't have so much instances of a moving horizon where multiple time steps. We had in the lab an example when we do unit commitment, for example, where we had to take repeated optimization actions, and MPC in this framework. In such a framework, very often what people agree upon is that what is interesting is not to find the optimal action that you have to take, but the optimal policy. What's the difference between a policy and an action? 40% of you had a course on MPC, so who dares an answer? Okay, it's Monday morning. An action is a control. Action means, for example, in the context of demand response, is setting the value of the power consumed by a heating system. Or in the case of a generator, it's setting its value in terms of produced power. That's an action. A policy is a mapping from state or disturbance, from something we observe, to an action. So a policy is giving the rules for which action we will do, and we're not saying in advance which action we will do, but we will let the system adapt to the current state and choose its action. We have seen examples of policies in the previous labs and in the previous lecture. We had called them affine disturbance policies, when we said, for example, that the generator set point was depending in a linear way on the total load. That was an example of a policy. MPC, so defining policies in general is the topic of stochastic optimization, and is, in the most general case, it's still an unsolved problem today. There are techniques to solve this in specific cases. In the most general case, it's a very difficult problem. One trick is MPC. The trick of MPC is, so the goal of MPC is to find a control policy. And what is this control policy? Well, it consists in doing the optimization repeatedly. So we'll go through that in several steps. So first, we need to cast the abstract framework. But I want to just to focus that compared to what we've seen last week, the policy obtained by MPC is more general than a linear policy. So this is a more powerful way to find policies. It applies to systems where we have, as usual, three types of things. We have a state, we have a plant that has a given state that depends on time. For example, the state is the state of an electrical grid. In the case of demand response, it's also the state of the thing that is consuming energy and that we're controlling. For example, if it's a building, a state would be what? Temperature. So there's a thermostat in this room, which I'm not sure works very well, but there is a thermostat and the state, it senses the state of this room, and depending on the state, it takes an action. If the temperature is below some threshold, it starts heating or cooling. That's an example of a state. The action is also called control, is what you will do that will influence the state. And there is something adversarial, which is classically called disturbance, which is very often considered as random, that is played by nature, whereas we play the control, and the result of all that is an effect of the state. So this mapping F is the model of the system we are controlling. So that's why it's called model predictive control. We assume we have a model that we know explicitly. So we're able to write equations that will say at time t+1 what is the result of applying action ud and nature playing disturbance dt when the initial state was xt. So that applies to systems that we can model in this way. Then we assume that in addition we want to minimize the cost, and the cost is assumed to be obtained after we have decided the control and after nature chooses a disturbance. So that's the classical way of formulating this. We're doing that in discrete time. So in discrete time, you always need to specify who plays what before, right? There is a subtle difficulty here in the t and t+1 in discrete time that does not occur in continuous time. Except for that, discrete time is much easier to manipulate than continuous time. So model predictive control is typically done in, is always done in discrete time. So we assume that at some control instant we observe the state. Based on that, we will choose a control action based on the policy. Then nature will choose a disturbance, and that will cause the state to become x of t+1. And then we will pay a cost that depends on where we are at time t+1, x of t+1. And also, typically, the action we take is associated with a cost. For example, if we are heating a system, by heating we consume energy, that has a cost. And our goal is to minimize the integral of the cost. So we have to formulate the problem in this term. If your problem is formulated in this term, then MPC comes for free. But we will see an example in the context of demand response. In this lecture, I will use as running example the heating of a house. This is David McKay's house. Who knows David McKay? Great. You know him for what?
I read the book, actually.
Okay. Can you recommend it?
Oh, yes, very much.
Okay. So I do too. So if that book has the good idea of being free, so it's available online. If you want a printed version, you'll have to pay. But if you want the PDF, you can buy it for free. It's called Sustainable Energy Without the Hot Air. And it's a catalog of quantitative things about sustainable energy. It's a large number of small topics. For example, it contains things that I borrowed there, which is a model of a house, a thermal model of the house with the parameters. So I took those parameters for his house here, which is, unfortunately, David McKay passed away last year. Before that, he was advisor to the British government for sustainability. And he had renovated his house, but as you may know, renovating an old house is a very difficult problem. So at the end, you come up with a half-insulated house. So we will use the parameters of this to do an example of demand response here. And the problem in this specific context becomes that assume you have a heat pump to heat these things, And demand response in many, as we will see in the next slideshow, demand response is very often implemented by variable prices of electricity. To incentivize people to consume at the right time, you change the prices. So now if the prices are variable, then you have to heat your house in a clever way, not just with a thermostat, but when electricity is cheap, of course. So we will see in this lecture how to do that with an MPC. So for that, we need a model of the plant. The plant is the house. And in our specific case, we assume this very simplified model that says that U of t is the amount of heat we burn in electricity to produce heat with the heat pump. That is translated by U of t epsilon, where epsilon is the coefficient of efficiency of the heat pump. And that this heat is put into the house and it serves to heat the house, but how much temperature is elevated depends on the inertia of the house, how thick the walls are and in which material they are. So this is captured by this coefficient. And then the heat you put in the house immediately starts getting out proportionally to the difference in temperature. This is the temperature of the house, which is now the state of our system. And theta of t is the outside temperature, which we can consider as a disturbance. That's a simple model. It's a simplified model that ignores a number of things, like what kind of things is it ignoring? Well, here I'm assuming the outside temperature is just used to control the amount of leak, how much energy we lose. But even in the UK, sometimes there is some sunshine that will heat the house for free. So there should be another term to say the heat comes from the heat pump, but also from the outside. So now, and there are other factors like the wind. If there's very strong wind, the leakiness will be larger. So there are other effects. And in the model we will do in the lab, there are more parameters that will complexify a bit the story, but the idea is exactly the same. So we will do in this slideshow this simplified model, which will allow us to understand all the concepts we need. Well, first, in order to use this model, we need to transform this continuous time physical model into something discrete. So we assume we take control actions at very small time steps, for example, every second, which for an electrical grid would not be very small time steps, but for a house or for heating, which has a large inertia, is a very small time step. So that gives us the discrete version of this, right? So essentially we're saying dt is t. This is the difference in temperature, T of t plus 1 minus T of t, and this little dt is a fixed delta t here. So this is what this equation would be, which I write in a more convenient form here by putting in the form that I had before, putting in focus on the state. The state at time t plus 1 is a linear function of the state at time t, of the control, the amount of heat I've added, and of the outside temperature, which is now the disturbance. Well, those parameters are deduced from the parameters of the house here. So this is the first step in using MPC. We need to have a plant model, which is now given here. We need also the cost. Now the cost has an obvious component, which is the price of electricity. When we consume U of t, we pay P of t. Here I'm assuming a house that doesn't have solar panels, that doesn't have a battery, so the price is the price of what we pay instantly. If we had solar panel and a battery, we would need more dimensions in the state. We would need, for example, the state of the storage, of the electrical storage, but this we won't do here. So that's the first obvious component. Now the trick, and where most of the, I would not say difficulty, but most of the elaboration you need on MPC is manipulating the cost to obtain something tractable. Here, our goal is what? Is to minimize our energy, the cost, minimize the money we will pay to the utility, And we think that this is also socially good because the utility is sending us price signals to incentivize us to consume energy at the times where it's better for the grid. So that's the obvious thing we want to do. But at the same time, we have a goal, which is to keep our house nice, comfortable, and cozy. So we need to have the temperature within some bounds. So depending in the UK, the temperature is perhaps 18 degrees. In Switzerland, it would be 21. So you have a temperature band in which you would like the temperature to be. So normally, what you would like is to treat that as a hard constraint. You would like to put in the constraints of your optimization problem that the temperature is here. It turns out if you do that, you have constraints on the state that make it complicated to solve. So what a first trick that is often used is called a soft constraint. We put a penalty function for the temperature to be outside the band here. And the penalty function can be anything, but your problem becomes considerably simpler if your penalty function is piecewise linear, which is what I did here. There is zero penalty if we are within the band, and then an increasing penalty for being outside or below here. If we're above here, we're just wasting energy. People will start opening windows. If we're below, it's cold, which is even worse, at least for comfort. So that's the mathematical description of this, and the visual description is this thing here. So when I have that, then I have all elements to do an MPC. And an MPC is simply this. It is repeated use of optimization. At every time t, I observe the current state. I predict the disturbance. So I will try to say something about the future disturbances. I can predict it in the form of point prediction or in form of a smarter form that contains some information about the uncertainty. It's called a prediction interval. Then I number crunch a large optimization problem that will give me the optimal sequence of actions for all future until some horizon that I call H. It's called the receding horizon. And then I will implement only the next action, U of t. And then at the next time step, I will do this again. That is what MPC is all about. So here I'm illustrating what MPC is in the analogy of driving a car. If you have autonomous car driving software, what you will do is at time t, you need to compute an optimal trajectory. So based on forecasting, for example, from the image, you can see how the lane is taking a curve. So the software computes the optimal trajectory, which is given by the green curve here. And then you implement at time t all the controls that should lead you here with the forecasted value of the disturbances. The disturbances are, in the case of driving a car, are the wind, the irregularity of the roads, the uncertainty about everything you have measured. I mean, you have measured the speed, the torque, the rotation moment, etc. But all of those are measured with some uncertainty. So if you think you will get here, in fact, you might get a bit at a slightly different point. And the idea of MPC is at time t, you compute this green trajectory and you implement all the controls that you think will lead you here. And at time t plus 1, you will look at where you are. You will see where you are. And from where you are, you will redo another computation of an optimal trajectory in the future and implement only the next step. That is MPC. Now, why is it a good idea? Well, the idea of MPC is it is combining two things. First, by taking a decision at time t, it is looking ahead in the future. It is seeing where you go. It's not just a myopic policy. So it's looking ahead in the future. But it adapts to uncertainty that is revealed after the prediction. So here the green trajectory is based on predictions that may be slightly wrong. At time t plus 1, you correct it. And because you do this correction, it is inherently robust without having to do robust programming even. So the principle of this is that by taking something like this, even if your optimization is not robust, you will have some form of robustness. What do I mean when I say even if the optimization is not robust? What's the difference between a robust optimization and a non-robust optimization in this context here?
We don't care about the disturbance. We are optimizing when it is non-robust.
We don't incorporate the disturbance. That's not exactly true. Here we will incorporate the disturbance, but we incorporate a forecast as if it would be exact. So we will have no bounds. We will not have intervals. We will treat the disturbance as something known in advance, so like an external parameter. So the non-robust MPC here is simply assuming that everything we know is fixed and I target this trajectory. A robust MPC would explicitly incorporate the uncertainty we have on everything. So we'll find a trajectory that perhaps is more conservative because you don't really know. So perhaps you would not go so close to the edge because you know there's uncertainty on my trajectory. And if I go past the edge, perhaps I fall here, there is a cliff or pedestrian sidewalk, etc. We'll see those differences. But the first thing to remember is by its very nature, by the fact that it uses a receding horizon and recomputes everything starting from the observation of where we are, this robustness is hardwired in the procedure. So even a non-robust MPC, in the sense of optimization, has some robustness that is inherited from the fact that it reconsiders everything at every step. All right. Questions? No. Okay, so let's do it. So first, we need to have some prediction of the disturbance, which is here the outside temperature. I call with a hat a point prediction. So we can take those point prediction for a weather forecast. So many energy management systems today are able to interface weather forecasts. And in fact, there's now a business of selling weather forecasts for the energy sector. If you don't have one, then you can simply look at the time series of the past years and have a less good forecast, but still something that would capture essential elements, like, for example, in May, during the night, the temperature is much smaller than during the middle of the day. And then we take so we are in the same framework as what we saw last week. So we have to do an optimization and define the cost. And here we take as cost the completely deterministic thing, assuming the temperature is the expected, is the point forecast here, which gives the following formulation. I have a horizon t. At time t, I have to minimize over u. So this notation, that's MATLAB style notation. It means the array of all values of u from t up to h values in the future. Since we start at t, that means from t to t plus h minus 1. And the state variable here will be a dependent variable, but it appears as one of the optimization variables given by this physical equation here. Theta here is not an optimization variable, is assumed to be an outside parameter given to us. And the cost is the sum of the cost of energy we will pay plus the penalty for the temperature. And since we had this equation written in this form, Ts plus 1 is 1 minus beta Ts. In other words, the control at time S gives the temperature at time Ts plus 1. I have to put Ts plus 1 here. So this is the optimization problem that we solve when we do an MPC. With the constraints that are here, simply the constraints on the control, that the control is between 0 and u max here. So this is how I formulate the MPC. An entire course on MPC would look at all the various ways of formulating. For example, if instead of putting the soft constraint here, I put it in the hard constraints, then I would have a different formulation of the MPC with different techniques to solve it. But this one is the easier, so that's the one we use it. So MPC style means at time t, we observe the house temperature. So the software of our controller observes the temperature in the house, computes the whole trajectory over, for example, h corresponds to 24 hours, solves the optimization problem, and sets the heat pump set point to the value computed here. Right. So I did that here over 2 days. So this is showing, in blue is the outside temperature. The forecast is the black dotted line. That was the forecast I had. The blue dotted line is the outside temperature realization. So there was small forecast error, as is customary everywhere. In orange is the prices of electricity, which are very typical of operators that do demand response. So you see that the electricity is inexpensive during nights and very expensive in the morning and in the evening, and has a medium price during the day, and is cheap again at lunchtime. This is very typical of what kind of grid? Well, this is more Spain than Finland. This means there is solar energy here. So if what happens now with the solar energy, the PVs, solar PVs that are deployed in many countries, I would say Germany also has a very large basis of solar energy. Even Switzerland starts having a decent one. Well, the peak production is at lunchtime. This is when the sun is high on the horizon. So the result of that is that usually there is more overproduction or than underproduction. At least the prices of electricity has dramatically gone down at lunchtime, which used to be a peak. But the downside is that there is very fast ramping towards the end of the day. So when the sun, solar PVs stop producing and everybody's returning home to cook spaghettis or other things, then this is where there's a high demand and a sudden loss also of all solar PVs. So there is a high price here. And in the morning, this is because everybody is using appliances at home. So this is a very typical price scenario. When we do demand response, those prices are assumed to be well known in advance. There are models where the prices vary, but it becomes very tricky to do demand response when the prices are not known in advance. So you want consumers to be able to predict when prices will be at which value to be able to have reasonable actions, right? So here that's also the assumption. So those prices are completely known in advance, which is, as I say, a reasonable assumption, at least over a horizon of a few weeks and months. And this is showing the evolution of the state with the MPC, which is the room temperature. This is a simplified example where those people want the same temperature in the night as during the day, which of course in reality would be different. So the penalty function would be different during the day and during the night. But here assume this is a room that is used 24 hours a day, and you want an average temperature, a temperature between 19 and 21. So we see here that the low price is used here to heat at maximum possible power to start the highest price period with a high temperature. Temperature is in some sense plays the same role as the state of energy in a battery. Temperature is the level of heat that is stored in a building. So when the price of electricity is high, you want to start that period with a high amount of energy in your building. So This is what the MPC is doing. The MPC was not instructed to do this. This is an emerging property of the MPC. The MPC decides to heat up at maximum here so that it can live through this period without buying electricity. And here we see the exponential decay of temperature that is happening here. Now there is again a low price period, so the MPC is heating as much as it can during this low price period, and then the temperature continues to drop because the building is not extremely well insulated. It's not poorly insulated, otherwise there would be, the decay would be much faster, but that I would say is a middle class building. And the temperature is getting too low, so it has to start heating even though the temperature is high, because here it has no choice, so it does it, it anticipates again here and starts heating before the high price period. And here, when the prices are low, it will not heat, but at the end here. So we see that during this period, also same thing here, it's very visible how the MPC is using its view of the future. If it did not have a view of the future, it would react to low price by heating here, for example. But here it knows there's no point heating here. It will heat at the minimum value required to keep the temperature as low as possible. And here we will heat to, because it anticipates this low cost, this high cost that comes in the future. And you see that the evolution is a bit different because the outside temperature is a bit different, but the control actions are very similar here. So this is what an MPC does. So if you compare the formulation here, the formulation is brutal. There is no intelligence. The intelligence of the system came when I am talking about it. I am observing what the MPC is. So that's the strength of MPC. It is able to find some policy that is what you would do as a human being, probably, if you think ahead, but it will do it thanks to having this ability to look ahead in the future here. The temperatures are the one I took from Mackay's book, except for the price for the penalty. Here I took 1 franc of penalty per degree of violation and per minute. So the time scale here is 1 minute in my example here. I said 1 second before, here it's 1 minute here. Here I'm comparing what I would do if I have a thermostat, like the thing in this room here. What is a thermostat doing? Well, it has a small temperature band, and when the temperature is below, for a heating system, it will start heating until and then lets the temperature drop, and etc. So it will give this pattern. Of course, the rate at which it drops depends on the outside temperature. When the temperature is getting warmer, then of course you don't need to heat a lot. But this is what thermostatic control would do. And the price in this example would be close to 8 francs, whereas the optimal price of the MPC was below 6 francs. So that's the main difference from a monetary viewpoint, which is the incentive for the energy management system that is running this MPC. And for the grid, the benefit is that we see that the consumptions have been, most of them, performed during the low price periods. So we can drive the usage of power by consumers by those price signals here, as the MPC is showing. Voilà, that's probably most of the story on demand response and the technology to implement demand response. We will see a few technical things on how to solve MPCs and what are the current tricks. Most of the tricks we've seen already last weeks. Those are optimizations, and the first thing that many people will try to do is to make things as linear as possible. This is what I did by having this form of the penalty function, because when optimization problems are linear, they are much simpler. We've seen a number of transformations to make problems linear, so let's recap. Here is one quiz on one of them. Okay, so I look at your solutions. So we have a tie for B and E. So let's eliminate things first. C and D are the same, right? That's fairly obvious. Maximize Z, subject to Z equal L of Y. Well, it's maximize L of Y, right? A, now, maximize epsilon subject to epsilon larger than L of Y. Well, since epsilon is unbounded, the maximum of this is plus infinity. So that is a non-interesting problem. Now it remains this one. So is this one the same as those? That would be answer B, or not. In which case it would be answer E, which is the second majority. Well, we can see that B is the same as C, because I want to find an epsilon that is larger than all the values of y, L of y, right? If you're larger than all of the values, you're larger than the max, right? And the smallest of those that are larger than all are the max, right? So this epsilon is the max of Ly, right? So it's the same as D, the value that you will find. The smallest epsilon is the max. So B is the same as D, C is the same as D, so the answer is BCD, which is answer B. We continue in the same vein. I close the poll. Well, it's a very important, this one is very important for optimization. So what we're doing in this course is not do a theory of optimization, but see how we use it for smart grid problems. And very often we have things like this. We have in an optimization problem, we have min and max that come. So how do we handle min and max? Well, the first thing to know is it's tricky. So, and this is visible by the variability of your answers. Now here, there's one way to think about it, which is to think of mice and elephants. Right. Assume you place on a square grid, a chessboard, you put mice and elephants randomly. You have as many mice and elephants. You have 64 slots. You have put 32 mice and 32 elephants. And that's a thought experiment, of course. It's very difficult to have a chessboard that's large enough to put some elephants, plus the mice stay in place and don't frighten the elephants. But assume you do this. And then you ask a question. So X is one dimension, for example, is the row index. And Y is the column index. And you call f of xy the weight of the animal that is at coordinate xy. Right. Now, what is the min A star? A star is obtained by taking first the max of the weights over one column. Now, there are big and small elephants, there are big and small mice, but the biggest mouse is always smaller than the smallest elephant. Right. Only in cartoons there can be an inversion, but in real life, a mouse is always smaller than an elephant. So when you take the max and you assume you have spread things on every row and every column, that's at least an animal of each type. So the max of this is always an elephant. Right? That's the weight of the largest elephant on this column. And then you take the min, which is the weight of the smallest of the largest elephant. So that's the weight of some elephant. Right? Now if you do the other way around, you take the min on a row of the weight, then you will obtain the weight of a mouse. Because on every row there's one mouse and one elephant at least. And then you take the largest. So you will have the weight of the largest of the smallest, but it's always a mouse. So you will have the weight of some mouse, not even the largest mouse, but the largest among those that was selected to be the smaller on every column, and vice versa for the elephant. But certainly, B star, which is the weight of a mouse, is smaller than A star. Right? So, which is, and you can prove in general this is true if you take the max of the mean, you obtain something that's always smaller than the mean of the max for every function of two variables, x and y. So that's a very general theorem. It happens sometimes that there is equality. If that happens, that's a theorem. It happens in some systems, and it's called a saddle point. For example, it happens to the Lagrangian when we write the Lagrangian of an optimization problem. We can take the mean with respect to the original prime and variables, or the max with respect to the Lagrange multipliers. And when there is strong duality, there is the mean is equal to the max. So we have strong duality, and that is a case where we have equality. When we have equality, we say we have a minimax theorem, but that is happening only in some specific systems here. So in general, that means take-home message, except if there is the min-max theorem, you cannot switch the mean and the max when you have the two together. They are not friends. The mean and the max is not the max of a mean. Take-home message. Voilà, we do a break and we resume at 10:15. We have seen that the mean of the max is always larger than the max of the mean. Now, how about the mean of the mean? And the majority thinks that they are equal, which is correct. If you think of mice and elephants, the mean of the mean consists in looking at the smallest animal on a row, which will be the smallest mouse on this row, and then taking the smallest of the smallest. So you will have the overall smaller mouse. And if you do it the other way around, you do it first by column, taking the smallest animal on every column, and then looking at the smallest, you will have the absolute smallest. So that works, absolutely. So it has a name in algebra. It's called the fact that minimum is an associative operation. If you have to take the minimum of a large collection of objects, you can divide and conquer and take the mean over every sub-collection and take the mean of the means. And of course, the same is true for max. So take-home message, yes, if you have means and means, it's associative. That means you can switch the order in which things are done, like we do in summations when we have integrals or summations. With integral, this formula it has a name. It's called Fubini's formula, the fact that the integral of f of x, y, dx, dy, you can integrate first with respect to x or first with respect to y. This is the same principle as here. So as long as you have only means or only max, it works. But as we have seen a few minutes ago, if you have a mixture of min and max, then you have to be careful. You need a minimax theorem for things to work. Voilà. Why did we do all those drills? Well, it is because, in my experience, the difficulty in implementing MPCs is in formulating the problem right and formulating the problem in a way that is exactly corresponding to something you can express, right? So very often when we see papers that talk about MPC, they say, here is my MPC, and then you wonder, why is it formulated in this way? For example, here, you often find papers that say, okay, I have to do demand response, therefore I will do bang, they do A, or they do B. And then you wonder, what are they really doing? So that's the question I'm asking you now. So the problem here is, how do we transform something that is expressed in the natural way into something that is tractable? And we have seen rules for transforming things that have nasty components like piecewise linear function, to transform them into things that are purely linear everywhere. We have seen in those 3 quizzes several transformations. The first one, which I call the max removal transformation. So the first thing here, when we say I have to maximize taking the max of L of y over y, then I can transform D into B where there is no max here. Instead, there is min. So I can remove a max by adding a variable epsilon in a global minimization problem. That's one trick. And the other tricks are the one we just saw before and the tricks of the previous week. So if you apply this and you try to reverse engineer which of A and B, if any, is a correct implementation of this problem. This problem is the one we have seen an hour ago. That's the problem of the software that's running an MPC, the energy management system of David McKay's house. So which one is the correct implementation? So that's a true example where those kinds of problems, I've seen them occur in real papers and in real homeworks. This is why I'm bringing it here. So what are we doing when we do A? In A, what's the difference? Well, we have put all the things as here, except we've replaced the phi, which is this piecewise linear function, by epsilon. Now the first step is to know that this piecewise is the max of three things. The max of the three linear functions. One of them is 0, and the other is this one, t minus t max, and this one is minus t plus t min. So those three functions. And I say epsilon is larger than those three things, those three functions here. But here I've put an epsilon, a single epsilon. So by the trick that we have seen in the first of the three quiz we did a few minutes ago, this is the same as replacing epsilon by the max of all those things. Now the max of all those things is the max over those three components and overall S. So when doing this, in fact, what I'm minimizing is this plus the max of the penalty. So what I'm doing here is minimizing the price plus the max of all penalties over my time horizon, which was not what I wanted to do. I wanted to minimize the sum of all the penalties, not the max. Not the worst penalty, but the sum of all. If I want to minimize the sum of all, this is what B is doing, because B has one epsilon for every time slot S, and this epsilon being larger than those three things, when we minimize over it for every epsilon, we obtain exactly the max of those three quantities for a fixed S, which is just phi of Ts plus 1. So 1 epsilon S at every time slot gives us exactly this here. So this is exactly the same as the original problem here. And while doing the transformation, of course, I'm studying a problem like this where I say this epsilon is the min of all those things, and I'm saying the mean of min is is associative here. So problem A, as I said, is maximizing this, which we can call a worst case penalty. Right? So problem A is not the one we thought we were doing. It's taking as penalty the worst of the penalty over all the time slots. Now you could argue, but perhaps this is also a good formulation of the problem. Perhaps we can argue, but the important thing to be able to do is to do the equivalence between one formulation, and that is interesting for the reader, for the designer of the system, and a transformation that's interesting for implementation as an optimization problem. So the transformation should be correct. Now we can discuss, is it better to do a penalty which is the max of all the penalties over my 48-hour interval, or the sum of all the penalties? Which one do you prefer? Is there any reason to prefer any one?
Should be sum of all the penalties.
You would prefer the sum?
If you take the max, there might be some outliers.
Mm-hmm.
And that won't give me the correct control.
If there is a max, you could not give the correct control. And that's true. I mean, there's two ways to look at it. I mean, first, assume during one, because remember, the time slot is very small. That's very typical of MPC. So every minute, I have one thing I compute. So if once during 48 hours, I have a 1 minute interval where I am above, I will pay the penalty. But given that I've paid the penalty once, whatever I do for the rest doesn't play a role. So if I'm outside the bounds, always during the 48 hours or once, is the same penalty with a max. Which means that probably you don't really control being in between the bounds. I mean, you accept in the nature of temperature, if you're outside the bound for a few time slots, which means if during 4 minutes of the day, the temperature is not exactly between 19 and 21, you can accept it. But if it's constantly outside, this is not what we intended to do. So if we reason about it, the soft bound, the soft constraint with a max would not make a lot of sense here. There's another disturbing thing is that you should always check how things are robust with respect to reparameterization, rescaling. For example, if I change my delta t from 1 minute to 1 second, does the thing change dramatically? If my problem changes dramatically when I change the delta t, then I have a problem. I mean, intuitively, when I discretize time, by taking a small discrete time step, I should have a good and accurate control. And if I make it much smaller, I should not improve. I mean, there should be a resolution below which it doesn't help to make it much smaller. Right? If that does not happen, then my formulation has a problem. Now, if I take the max over a period of time, and the period of time shrinks, then the max also varies a lot. Right? If I look at the temperature every second, for example, there's 1 second where it's outside the bound. When I average over 1 minute, or if I subsample over 1 minute, I might not see that at all. Now, if there is 1 second where I'm outside the bound, because I have a penalty, anyhow, the optimal control will not care about the bounds anymore, and that is dependent on the time, very dependent on the time slot I have. So that is confirming that that would not be a good thing. So take-home message. When we try to linearize things, we make them piecewise linear, and if piecewise linear things are convex, they will appear as max of things. And we can always remove the max by replacing, whenever there is a max in an objective function that has to be minimized, by a min. And since we have means of means, by using associativity, we will get a nice problem here. Last item we will look at is what happens if we want to still make the problem robust. Robust in the sense of optimization. So as we discussed an hour ago, the robustness here assumes we don't take the temperature as certain for the future, but we take them as given within some uncertainty set here. If we are able to formulate that, we obtain what we call a robust optimization problem here. Well, first, the good news is that this is nothing different than what we did in the past module. Just means we have an optimization problem where the constraints may have a quantifier. For example, here I'm assuming that at every time s, there is an upper bound and a lower bound and an upper bound for the temperature, which is given here by those ranges. If you have a sophisticated weather forecast, this is what you will get. You will get not just a point estimation, but also some quantification of the error bound. Here the error bound is very brutal. It's almost constant. That if you have more sophisticated prediction models, it might not be as nice here. So now if we want to incorporate this, that means that the optimization problem will be formulated in this way. We will have that I call T sub the temperature at time t is now a function of u and theta, where theta is the whole set of disturbances of temperature. And my temperature in the MPC is equal to the temperature at time t. The MPC, remember, starts at time t, and then try to optimize things for the future starting at time t. So at time t, I take the optimal, what I have observed, and then in the future, the value of the temperature, which is the value of the state, if we use the general language about control systems, the state in the future will depend on the set of control decisions I've taken and the value of the disturbances. And they are given by those equations that I have here. Right? So this is the problem that we will have to solve. Now, we don't know what the temperature theta will be, but the only thing we know is that the temperature will be between those two bounds here. We can first use the set of tricks that we have used, that we have seen before. First, we can replace the max of affine functions to make everything linear, so that we have now to minimize these linear objective functions subject to, those are our controls. So the controls are that they are between the max capabilities of our heating systems. And then our auxiliary variable, epsilon s, is larger than the internal temperature that depends on theta. And now, this must be true for all values of the temperature that are in the uncertainty bound. So theta here is a compact notation. That means the whole trajectory of temperature from time t to times outside temperature, from time t to time t plus h minus 1. And this set theta is given here. Right. So in this compact form, we recognize exactly a robust optimization problem in the form that we had seen last week here. Except here the Ts plus 1 is not made explicit. Ts plus 1 of u t is the temperature at time s plus 1 if the controls are u and theta, which is obtained by recursively solving the state equation over multiple time steps. So we can use the same tricks as last week, using methods for removing the theta, which involves solving auxiliary optimization problem. And in the worst case, we will have to use duality. But in the case of receding horizons, there is very often a structural property that will simplify this. And this is the property that we will see now. So here I'm just reusing exactly the tricks we've seen before. The epsilon s being larger than all those values mean it is larger than the max of those, which gives this formulation here. Epsilon s larger than all the future temperatures and larger than, yes, this thing here. So what's the difference between the two? Elimination of all theta. Yes, I've just pretty printed those things. So using the elementary but important transformations we've used many times, that's the problem I have to solve. And this is where we could use the tricks of last week, but now there is an additional property that very often occurs when we have receding horizon things. It's a monotonicity property, which is also often called isotony. Isotony is a property of a mapping. A mapping, well, what is the mapping here? Now, the mapping is, in this problem, I have to choose the sequence of controls, and nature will choose the sequence of outside temperatures. Now I'm interested in knowing, if I choose a given control, how does the state, which is the inside temperature T, depend as a function of the choice of my adversary, that is nature, which is the outside temperature. Well, in this case, there is a monotonicity property, which is the higher the outside temperature is for a given control. If my heating decisions are fixed and all the same, now if nature plays a certain some outside temperature, the higher the outside temperature, the higher the inside temperature will be. At least that seems to be reasonable, right? If you set the heating action to number 2 on your heating system, if it becomes warmer outside, then the inside temperature will be warmer compared to if the temperature outside remains cold. Right? By the physics of the system, the heat goes from cold to warm. Of course, we will need to demonstrate that, but that property is called a form of isotony. So what is an isotone mapping? Here the mapping is the mapping that maps the sequence of outside temperature to the temperature, the sequence of inside temperatures, right? And isotone means that if the entire sequence of outside, if I have 2 sequences, 2 inputs with apex 1 or 2, and if one is consistently smaller than the other, over the entire trajectory, the first temperature is less than the second, then the same will be true for the inside temperature here. Right. Which seems intuitively clear for this system. Will need to be demonstrated formally, but seems to be clear for this system. Now, in our robust formulation, we had to compute things like what is the worst case of the temperature at time S over all possible outside temperature. Well, the isotony property means that, well, it is obtained for the upper bound of all the temperature. Because any theta that nature will play at every time S will be less than theta max S. That's the assumption I'm making. I'm making the assumption here that at every time S, theta S is less than theta S max. So if I take this as my first possible play of nature, and here the second play of nature, then if nature plays 1 rather than 2, the internal temperature under 1 will be less than under 2. So I'm just saying in a formal way that the worst case for the internal temperature is when the external temperature is the higher. Therefore, the max of the internal temperature is the temperature of the theta max. Now that's very good, because here I had something with a quantifier for all possible value of theta, and now this is completely removed. And similar for the mean. The mean inside temperature will be obtained when the outside temperature is the mean. So if you remember how we had transformed our problem, we had this property. Epsilon S had to be larger than the max of the internal temperature. Now we know what that thing is. This is the value of the temperature when the outside temperature is theta max. Which gives the following. I need to say that epsilon S is larger than the value we obtained for theta S. So I have a set of auxiliary variables, which are now those, Ts plus 1 of u theta max, now that are computed by this equation. Ts plus 1 are given by this state evolution when the outside temperature is theta max, and similar for min, which gives us this following transformation. This is our linear formulation of our MPC, where I have incorporated the robust conditions. So you see that we have epsilon S less than Ts plus 1 max. So Ts plus 1 max is the temperature at time S plus 1 when the outside temperature is theta max. And I can treat that as a set of auxiliary variables that follow the state equation of the system when the outside temperature is theta max. But I need also to track the converse worst case, which is when the temperature is min, that gives us a Ts min, and I need epsilon s less than Ts plus 1 max minus T max, because I had a max in the first transformation. And here I had a min, so here I look at the min here. So I need to considerably augment the number of variables, but this is simpler than using duality or other methods that we had done before. This is how I would make my formulation robust. And if I do that with exactly the same outside temperature, but with these outside temperature bands that I knew in advance, here is the trajectory of the temperature. We see the control actions are very similar. We always use maximum power at the end of the low price period. But do you see a small difference with the non-robust version? Well, if you look at the cost first, so if we look at the non-robust version, which is here, the cost here is less, which means the robust version costs us something. By being robust, we were more conservative, and by being more conservative, we are more expensive, but we are more robust. That means we take less risk, and it's visible why where we took less risk. We see here, for example, that we stored less energy in the building. We could have gone in the non-robust version, we'll go to the max temperature. Here we will not. Why will the robust version not do that? Exactly. It thinks there is a risk due to the uncertainty on the temperature here. If the temperature suddenly jumps here, I could have a larger, I could violate the penalty and pay 1 franc for the violation. So instead of accepting that, I prefer to be a little more conservative, and then I pay 1/10 of a franc in average over in integral over the whole period. So this is how a robust MPC will work. Now you could argue, is it a good idea to be robust? Well, first we see there is not much difference. It depends on how complex your system is. When a system is as simple as this one and the violation is not a hard violation problem, then the robust formulation might be an overkill. But in some other cases, it might make a difference. I said that intuitively, it's clear that the higher the outside temperature, the higher the inside temperature for a given control. If it's obvious, it should be proven easily. If it's not proven easily, perhaps it's not so obvious. So let's still do the proof. So the thing to prove is that if I have 2 sequences of outside temperatures that are in this order, one is consistently less than the other, then, and the 2 temperatures start from the same initial value, then they will be in the same order during the whole evolution. So that's obviously something to be done by induction. So this is true at the original step because we start from the same value. And then we look at the evolution equation, which is given by this. I take the difference between the first minus the second, and I want to see whether this will be negative. Then I obtain that it is 1 minus beta, the difference of the temperature at the previous time step, plus beta, the temperature, the outside temperature. Right? Now, by hypothesis, this is negative. That's the hypothesis that sequence 1 is less than sequence 2. And by induction step, this is negative. So the key thing that make it work is that the coefficients here are non-negative, which means beta is between 0 and 1. So the key thing is that the coefficients in the evolution here, the controls are fixed, so the coefficients of the control do not matter, because when I compare the 2 sequences, I have the same controls. But the key thing that matters is that the coefficients of the internal state and of the outside disturbance are non-negative. Whenever I have a linear system where those coefficients are non-negative, I will have an isotone system, and I will be able to do the robust case in this way. Right. Voilà, that's all the technique we will do for MPC formulation. Let's recap with a small quiz. Is any of those two formulations a correct formulation of the small MPC that we see for this toy house? And the correct answer is D. But it's a good drill because that's exactly where the difficulty is. So we see we have a relatively simple example. We have David's house, a single dimensional state. The difficulty of MPC is because we have time that multiplies the number of variables, is to make sure we don't get entangled in the many variables and make a mistake here. So here I'm saying at every time S, the temperature follows the equation here for any value of the disturbance theta. But this is impossible. I mean, for a given theta, you have a different constraint. For different theta, you have different constraints. So the set of feasible capital T that will satisfy that is empty. So if you ask MATLAB to solve this, it will return infeasible. It will say infeasible. And then you will wonder why infeasible, okay? It's not because the problem is not feasible. We've seen in last week that there may be infeasible problems because of the robustness constraint or because there's no operating point that satisfies all the constraints. But here it's a bug in your formulation. You're saying the temperature the inside temperature must satisfy that for all, which is true, but in this formulation, T should be a function of the temperature, not an optimization variable. And we've seen how to get rid of this in the previous case here. So this is not a correct formulation. B looks better. There is not that problem because there is not the quantifier for all theta. But what is B doing? B is saying theta satisfies this and the temperature satisfies that. So this is all correct. But when we pose the problem in this way, what are we doing? We are choosing theta. Right? So this is an optimization problem where you choose your control and you choose the disturbance. You choose the outside temperature. Of course, if you can do that, if you're in winter, you would choose theta equal to T max, theta max, and because that will be the cheaper for you. But that does not correspond to the true problem we had. Right? The true problem we had is none of those. Here. The true problem we had in the true formulation that we saw a few minutes ago introduced an intermediate function, Ts of u theta, that disappeared in the constraints because we took only the max and the mean, and then we replaced the max and the mean by additional optimization variables. Here. Is there anything else? Yes, okay. So in conclusion, from the theory of optimization, MPC is a straightforward application. But because it multiplies the number of variables, we'll try to make it linear in many cases. Making it linear will involve all the transformations we've seen. And the MPC will be inherently robust. We can even make it more robust using the robust programming techniques. And one particular trick that is often usable here is to use monotonicity properties. Voila, the next step for this is to run this on the 35 dimensions of the house model we have in the lab. But the difficulties are the modeling difficulties. Now there's a bit of programming. You need to have MATLAB. For the lab we will use YALMIP. That gives a higher level interface for programming. But the difficulty is to express the program to do exactly what you think it is doing. And we've seen that it's full of traps. There are many ways we could formulate a problem that seems reasonable and is not doing what we did. But we've seen the rules to help us do a thorough and sound transformation. It's the rules of how we manipulate the means. The means are associatives. We can remove the max by this trick of introducing auxiliary variables that are lower bounded by all the constraints. And when we've done that, we have removed the max, so we have only means, and we can use associativity. Questions on those technical parts? No? Then I'm sure they will come during the lab. So right now we continue without further ado to discussing the interesting part of all that stuff, which is demand response.